This is the Pythagorean Theorem, and even people who are not great fans of mathematics might remember the formula from their high school studies. Calcea Johnson and Ne'Kiya Jackson, two remarkable high school seniors from New Orleans East, made national and even international news for developing an ingenious new proof of the Pythagorean Theorem. As I record this in 2023, it's been a little over a month since the story hit the news. I don't know these young women, but I am a high school math teacher in New Orleans, so I was especially inspired by their achievements. At this time, Miss Johnson and Miss Jackson have not published their proof yet, but some news sources have included images from the presentation that they shared at a recent American Mathematical Society meeting, and from there, curious math enthusiasts have deduced how their argument apparently goes. I had some concerns that such speculation might undercut their work since they haven't yet gone to publication, but I'm at least encouraged by the abundance of positive attention that has come their way. Even the speculation regarding the details of their proof is generally presented in a way that seems intended to fully give Calcea Johnson and Ne'Kiya Jackson the credit they deserve. Now, the Pythagorean Theorem is one of the most, if not the most, proven math theorems in history. A book published in 1940, titled The Pythagorean Proposition, compiles several hundred varied proofs. Calcea Johnson and Ne'Kiya Jackson weren't claiming to tell us any new conclusions about how the legs of a right triangle relate to the hypotenuse. Their goal was to find a not yet traveled path to that well-known conclusion of a squared plus b squared equals c squared. One of the things that makes their proof noteworthy is that it is largely based on a trigonometry formula called the law of sines. This defies a claim made in the Pythagorean proposition that there are no trigonometric proofs. That claim curiously states that all of trigonometry is based upon the Pythagorean identity specifically, which itself is based upon the Pythagorean theorem. Therefore, employing trigonometry in a proof of the Pythagorean theorem would allegedly result in circular reasoning, which is not allowed. I don't believe there's any dispute that the Pythagorean identity or any other trig formula that depends on it may not be used to prove the Pythagorean theorem. However, Calcea Johnson and Ne'Kiya Jackson didn't buy the notion that all of trigonometry rests on that one identity. I am certainly among the many who would agree with them. The definitions of sine and cosine are the fundamental building blocks of trig. No problem with those. The law of sines may be easily proven without anything Pythagorean, so Johnson and Jackson felt at liberty to use it in their proof. It's worth noting that much of trigonometry focuses on right triangles, but the law of sines applies to any triangle, regardless of whether it includes a right angle or not. Now, I would concede that there are some trig formulas that occupy a gray area, for me at least. A friend of mine started with Johnson and Jackson's apparent proof, and then found a variation that uses this sum identity, in place of where they instead made clever use of an infinite series formula. While the sum identity may also be proven without using the Pythagorean identity, it's a formula I'd rather avoid in this pursuit. My main objection is that the sum identity all by itself can very efficiently prove the Pythagorean theorem. Notice that if alpha and beta are complementary to each other, they add up to 90 degrees, and we can plug in these basic definitions up here, and out pops the Pythagorean theorem. So in my opinion, the sum identity is among those trig tools that isn't outright illegal to use in a proof of the Pythagorean theorem, but to me it still feels like cheating to use it. So, completely inspired by New Orleans' own Calcea Johnson and Ne'Kiya Jackson, I wanted to dive into the challenge of finding another trigonometric proof of the Pythagorean theorem. And eventually this past week, while students at my school were taking a standardized test, I spent some time wandering the trigonometric landscape and eventually found a proof myself. To be clear, I in no way want to steal any of the accolades that Johnson and Jackson are receiving, and anyone who looks at both of our proofs will almost certainly agree that their proof exhibits a certain elegance and conciseness that mine lacks. But I also experienced the rush of excitement that those two young women must have felt when that famous formula first emerged from their calculations. So I'll share my findings here. I'm going to start with a generic right triangle, labeled in a fairly typical way as you see here, but with the added condition that acute angle alpha is less than acute angle beta. Alpha and beta, you see, are the measurements of the angles at vertex A and vertex B, respectively. And that would also lead us to conclude that side length A must be less than side length B. We see that sine of beta equals this opposite divided by this hypotenuse. Let's go ahead and tuck that away over here. I then reflected the entire triangle across its longer leg, labeled as you see on the screen here. And I should mention, this idea was borrowed from the work of Johnson and Jackson. That's exactly what they did. And just like them, I'm going to apply the law of sines to this entire isosceles triangle, A, B, B prime. So, law of sines tells us that sine of this angle, 2 alpha, divided by the length of its opposite side, and that has length 2a, is equal to sine of this angle, beta, divided by the length of its opposite side, c. We've already established that sine of beta equals b over c, so let's sub that in. B over c, and that simplifies to b over c squared. So now we can multiply this 2a over to the right side of the equation and be left with sine of 2 alpha equals that 2a times b over c squared. Let's take that equation and move it over here. Up to this point, I've done nothing original. This appears to be the way that Johnson and Jackson started their proof as well, and I've just borrowed from them. But at this point, I started feeling like I really should steer off in a different direction. So while Johnson and Jackson then started drawing an infinite series of similar right triangles down below this isosceles triangle, I decided to reflect the original right triangle across its hypotenuse. And from there, I extended a couple of the line segments out until they intersected each other. Let's say that intersection occurs at vertex D. And let's say the length of this segment is x, and the length of this segment, let's call that y. Just to be clear, x is the length from vertex C prime to D, and y is the length from vertex B to D. To figure out the measurement of this angle, let's consider that from our original triangle, we know that alpha and beta measure complementary angles. In other words, alpha plus beta equals 90 degrees. Well, if I double that equation, I get 2 alpha plus 2 beta equals 180 degrees. And we see that here we have a measurement of 2 beta. And we know that 2 beta is a linear angle along with this angle that we're trying to find. Linear angles add up to 180 degrees. We know that 2 alpha plus 2 beta also adds up to 180 degrees. So that means this angle must be 2 alpha. Let's now turn our attention to this triangle right here, with vertices at A, B, and D. Specifically, let's consider the area of that triangle. We know the formula for the area of any triangle is area equals 1/2 base times height. And we could apply that formula to this triangle in a couple different ways. We could consider this side to be the base, and therefore we'd have 1/2 y, and this length would be the perpendicular height. Therefore, we would put a b here. But we could also consider this entire length to be the base. That's x plus b, right? So 1/2 x plus b, and in that case, this length would be the height. So we'll put an a here. We can now rearrange that equation. We can divide out the 1/2s, and we can say, let's take this y here and divide by this x plus b, and that should equal this a divided by this b. It's worth noting we could have also developed that same equation by applying the angle bisector theorem to this angle, which is being bisected by this line segment. Y divided by x plus b equals a divided by b. Angle bisector theorem. That's actually a little quicker, isn't it? Either way, let's take this equation and move it over here. Let's now turn our attention to this triangle right here, with vertices at A, C, and D. I'll admit at this point in the process I was kind of just grasping at straws, trying to write down any equation I could that might be promising. Since that's a right triangle, we can apply our simple definition of sine. Sine of this angle with measure 2 alpha is equal to the length of the opposite side. That would be y plus a being the length of this side, divided by the length of the hypotenuse. That would be x plus b. And at this point, we might notice the similarity between this expression and this expression over here. So that might compel us to split up this into two different rational expressions. Y over x plus b plus a over x plus b. And from here, let's substitute in a couple other expressions. We know that sine of 2 alpha equals 2ab over c squared. So let's put 2ab over c squared in for sine of 2 alpha. We also know that y over x plus b equals a over b. So let's sub that in. Don't really have anything to sub in here, so we'll just keep it as a over x plus b. So, what to do from here? Well, when we keep in mind that our ultimate goal is to churn out the Pythagorean theorem, that only includes a's and b's and c's. We don't want to include these other unknowns, x and y. So that compels us to solve this equation for x. I'm going to do this all in one step, see if you agree with me. I'm going to say that x, when isolated by itself, equals this a divided by this 2ab over c squared minus this a over b minus b, this b specifically. And if I multiply this first expression by bc squared over bc squared over a, there's quite a bit of canceling, and what I get in the end is x equals bc squared divided by 2b squared minus c squared, and this minus b at the end is still just hanging out there. Double check all my algebra, make sure you agree, and if so, we'll go ahead and put this over here. So, having just gotten x in terms of b's and c's, it seems to make sense to go ahead and try to get y in terms of a's and or b's and c's, right? And again, I'll admit at this point I was just trying to churn out a lot of equations, didn't know if this was going to lead anywhere. But what gave me a glimmer of hope was that I was starting to see b squared, c squared, another c squared here. That's starting to look a little bit like the Pythagorean theorem, isn't it? That's what compelled me to just keep going. To get y by itself, I started with this equation and multiplied the x plus b over. That gave me y equals a over b multiplied by that x plus b. And from there, I substituted in this expression for x. And I got a pleasant surprise there. I was initially a little bit annoyed by this minus b hanging out at the end of that expression for x. But look at how nicely it cancels out this plus b here. So at this point, minus b and plus b subtract each other out, and I also see that this b divides out this b, and that leaves me with y equals a times c squared divided by 2b squared minus c squared. Let's add it to our collection over here. And if you're starting to get wary of all this, wondering when is this all going to conclude, hang in there, we're almost there. Finally, we're going to turn our attention to this right triangle with vertices at C prime, D, and B. Because we once again see an angle with measurement of 2 alpha, you know what we're going to do with that, right? We're going to take sine of 2 alpha one more time. For this right triangle, that would be opposite x divided by hypotenuse y. And from here, we plug in those expressions for x and y. To resolve those fractions within fractions, we're going to multiply by 2b squared minus c squared over itself. And that gives us bc squared minus b times the quantity of 2b squared minus c squared over ac squared. And from there, let's do one more substitution for sine of 2 alpha. Let's go to this equation, and one more time replace sine of 2 alpha with 2ab over c squared. On the right side of the equation, we'll take this bc squared And we also see that there's another bc squared. We see negative b times negative c squared, so that gives us 2bc squared. And then this negative b times 2b squared gives us a minus 2b cubed over ac squared. And here it comes. Look at how similar those denominators are. Let's go ahead and multiply the left side by a over a. So that would give us ac squared on the bottom and 2a squared b on the top. From there we can multiply both sides of the equation by ac squared. And when you notice that all three terms in that remaining equation have a greatest common factor, do you see what we get when you divide out that greatest common factor, which happens to be 2b? Dividing this by 2b gives us a squared. Dividing this by 2b gives us c squared. And dividing this by 2b gives us minus b squared. Rearrange that to get a squared plus b squared equals c squared. That's our Pythagorean theorem in all its glory. Not the most beautiful, not the most elegant proof of the Pythagorean theorem that you're ever going to see, but I'll still claim it as mine. And again, credit to Calcea Johnson and Ne'Kiya Jackson for coming up with a proof that I think was superior to mine. But I'm still proud to put mine up along with theirs in the ever-growing collection of proofs of the Pythagorean theorem. It has been pointed out that, contrary to some of the news coverage, the Pythagorean theorem actually has been proven with trigonometry prior to this year. While it may not be quite accurate to say Calcea Johnson and Ne'Kiya Jackson were the very first to have ever done that, this point does not detract from their impressive feat. Their proof, or at least what is speculated to be their not yet published proof, is extremely clever and worthy of all the positive attention it's been getting lately. My intent in making this video was simply to document for myself and share with anyone who might find it interesting how these wonderful young scholars inspired me to re-engage and re-examine the Pythagorean theorem. As much as that famous formula has been studied by numerous civilizations and countless brains over the millennia, how exciting to find that it still has mystery and adventure to share. We school teachers are tasked with leading the way in the mathematical journeys of young people, but how thrilling are those occasions when they turn it around and inspire us to grow in our own development. Big thank you to Calcea Johnson and Ne'Kiya Jackson for showing us what you can do.